All right, so if you're looking for even more NMR practice problems, this is a good website to use, webspectra.chem.ucla.edu. You can see some, useful links, that kind of thing. You can see some types of NMR, notes on NMR spectra, table of IR absorptions, that kind of thing. And then they have a whole bunch of practice problems. You can see they've got a whole boatload. We're going to stick to this beginning one, so don't move beyond the beginning one. There's 28 problems, which should be way more than enough. So let's just go ahead through one and see how it goes. So we'll start off with number 19 here. You can see that number 19, along with the NMR, it also has an IR spectra, so we'll see how that works out. So you click this here, and then you get a whole bunch of stuff, right? You can view the solution right there. Don't view the solution until you have a pretty good guess of what it is. So let's check out the IR spectrum first and identify some important peaks. Right, so we have our IR spectra right now. You want to pause the video here and take a, think about what the important peaks are. Below 1500, we ignore all that, so we don't have to worry about anything below 1500. If we look over to this 3000 area, we've got some interesting peaks right here. We can see our broad OH peak. And so let's draw kind of number 19. Think about what the IR tells us. The IR tells us that there's an OH peak, right? And then we've got some peaks beyond 3000, right? So that's going to have some alkenes in there with some H's. And then if we click zoom out up top here, can zoom back out. And then we can see we also looks like we have some C double bond C peaks there, right? Same thing that we got from the CH. So that's pretty much all we can pull from the spectra. Another thing that this website will give you straight off the bat is the formula, right? So this is C8H10O. So we kind of broke one of the rules and we didn't do that part first, but that's okay. H10O, right? And so there's our formula. Next thing we're going to think about degrees of unsaturation. So you can use that equation if you'd like. That's definitely useful. And so this could have up to 18 hydrogens. It only has 10, so that means we have 4 degrees of unsaturation, right? And anytime we have 4 degrees of unsaturation, what we're thinking about is maybe a benzene ring, right? Maybe we have a benzene ring here. And something from the IR tells us that we have double bonds and H's, so that's another clue pointing towards a benzene ring, right? So we've got more evidence towards that. Let's go ahead and click back to problem over here. Now we're going to check out the carbon-13 NMR. We're going to check out the carbon-13 NMR first because it's a simpler spectra. And so we want to start off with kind of the simple data and then go on to the more complex data. So here's our carbon spectra. You can see we don't have anything beyond kind of, let's see, like 150-ish. So let's zoom in here to about 150. And then our first peak shows up at like 40. So let's zoom in at like 30. So I'm just going to take an image of this because I want to show you something on this. So I think pretty much all of these NMR spectra have been taken in a solvent of deuterated chloroform. And the solvent peak from deuterated chloroform shows around 77. And it's it's 3 peaks for the solvent, right? So always ignore this kind of triple peak here. And so we've got 1 carbon here, another carbon there. We can see those 2 are in not the double bonded area, right? So those are probably just some alkyl chains. And then we've got all these peaks here. You can tell it's difficult to tell how many peaks exactly are in here. So let's go ahead and zoom in a little bit further. So let's zoom in between 150 and let's go with 120. Zoom in there. Okay, and then it looks like we got 1, 2, 3, 4 peaks. So 1, 2, 3, 4. I'm going to relabel these guys as number 5 and number 6, right? So we've got 6 carbon peaks, but we have 8 carbons. And so we know we have some sort of symmetry, right? Because we have 8 carbons, but we only see 6 peaks. And then what we also notice is that we have some in this aromatic C double bond C range. So again, that's kind of, we've gotten evidence from IR, the degrees of unsaturation, and now carbon-13 NMR are all pointing towards having this benzene ring. I don't think there's too much more useful information we can pull out here. So let's go ahead and go to the proton NMR. All right, so Proton Nmr, first thing we notice is that we do have peaks in this benzene region. And so we've got a whole bunch of clues that tells us that benzene is here. And so it's a pretty good guess that we have some kind of benzene ring here, right? And then another clue that we want to use is how many hydrogens are located in this aromatic region. So let's go ahead and zoom in a little bit. Let's go from like 8 to 2. Should have things be a little bit easier to see. And we're going to kind of go over one tricky thing that I didn't quite cover, that none of the books cover, so that's a little interesting, but we'll go over it here. And so you can see it's a little bit difficult to see, but you can see these integration peaks right here. This one goes like that, 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 and then this one goes like that. And so we're thinking about, all right, which one of them is the smallest? This one's our smallest one, so we're going to call that 1. Both of these guys seem to be 1.5 times the size, so 1.5. 1.5. This one is also to the left here, 1.5. And then this one looks to be about 3 times the size, or maybe just twice. Yeah, we'll go twice the size of this other compound, right? And so we can't have 1.5 carbon, so we have to round it up, right? So this has to go to 3, this has to go to 3, this has to go to 2, this has to go to 4, and then this has to go to 3. And so then if we add up all of these carbons, or all these hydrogens, my bad, 3 plus 4 is 7, plus 3 is 10, 13, 15 hydrogens. And so if we take a look at our formula, we only have 10 hydrogens. So what's going on here? Let's go ahead and check out our smallest peak. From about, let's zoom in from 3 to about 2. And so if we look at our smallest peak, you can tell it's quite broad. And we know that we have an alcohol from our IR spectra told us that we have an alcohol. And so we're thinking, all right, this broad peak is probably the alcohol peak. And so here's another thing about the alcohol peaks that we previously didn't go over, is that they don't always integrate to 1. Because we can have exchange, they're sometimes going to disappear a little bit. So even though it represents 1 proton, it might not integrate to 1. And so what we need to do is we need to erase all of this data. We need to say that straight up, this is 1 hydrogen. And because we only have 1 oxygen, so we can't have multiple alcohol peaks. And so that's 1 hydrogen. And then we need to go back and say that now this is our smallest peak, right? So that represents 1. This is the same size, 1. This represents 1. And then this is 1.5, right? It's about 1.5 times the size. Can't have 1.5 carbon, so we have to round up. 2, 3, 2, 2. So add those up. 2 plus 3 is 5, plus 2 is 7, plus 2 is 9. And then add in our 1 alcohol peak. We get 10 hydrogens, which is exactly how many hydrogens we should have, right? So we've gone ahead and clarified that point, so that's good. Let's think about what else we can pull from this data. We have 5 aromatic protons. The only way we can have 5 aromatic protons is a monosubstituted benzene, right? So we know we have that point right there. And then we also remember we know we have an alcohol, right? And so if you think about putting an alcohol right on here, that would end the chain, and we still have 2 more carbons to use up. So there's got to be something between the benzene ring and the alcohol, right? And we saw 2 carbons in the aliphatic region. So that's kind of another clue. So let's go ahead and zoom out again, and we're going to zoom into this peak between 4 and like 2.5. So let's go to 4 and 2.5. So we see 2 things. There are 2 triplets. So let's just redraw it, right? We've got a triplet. And then we've got another triplet. And before we said that they both integrated to 2 hydrogens. So if you think about a triplet, it has 2 neighbors. And this other one then has 2 neighbors. Well, they're the only hydrogens that are left. So if they are each are two hydrogens and they have two neighbors, they must be each other's neighbor, right? And so we know we have a component that looks something like this, right? Where we would end up with two H triplets, right? And so we've got an R group over there. Go ahead and erase this part. We've got an R group over here, and we've got an R group over here. The only thing we need to figure out is how we're going to stitch them together. And really, there's only one way to do this, right? This R has to be connected to one of these R's, and this R has to be connected to this other R. So when you put it all together, we get this compound right here, right? And there's many things that tell us that this is a compound, right? We saw our alcohol peak in our IR. We calculated 4 degrees of unsaturation, which pointed us towards the aromatic carbon. We saw aromatic carbons in the carbon NMR. We saw 5 aromatic protons in the proton NMR. And then we saw a set of, we saw 2 aliphatic carbons in the carbon NMR. And then we saw 2 H triplets in the proton NMR, which indicated that it was these two, right? So this is the final answer. And again, these are really like puzzles. So it's kind of difficult to make instructional videos of how to solve these problems because each problem has their own little unique quirks in it. And really the best way to get good at this is to just practice, practice, practice. So do a couple of practice problems, see if you get them. If you don't get them, then come to my office hours and we can work through some of these thought processes together. But you really got to practice in order to get it.